welcome back, and I hope you had a good coffee break and now recharged. First of all, I'd like to thank KK for inviting me to chair this session. It's really my great honor to chair this session, particularly with Sir Michael speaking. Before I give a little bit more formal introduction, I'd like to let you know that this is not the first time Sir Michael visited Singapore. He was here 29 years ago, twice, in 1989. The first time in March and the second time in December. And in December, he came as Lee Kuan Yew distinguished visitor. And he gave a public lecture, of course, in addition to some technical ones. And he attracted more than 700 people attending his public lecture, which was entitled Beauty in Mathematics. And I think you still talk about beauty in mathematics, right? And I remember that the hall was packed with people. Many were standing on the sides and many were sitting on the steps. And that was a very fantastic, very excellent public lecture. And I'm very happy to see that, to have Sir Michael back in Singapore again after 29 years. Am I right? Have you been back here in between? No, 29 years. Okay. Now, well, I hope I won't take too much time, but there are certain things I really have to say about Sir Michael. So Professor Sir Michael Atiyah is well known for establishing the index theorem jointly with Isidore Singer. Heralded as one of the landmarks of 20th century mathematics, the index theorem has had far-reaching impact in the fields of both mathematics and physics. It has also led to important new links between analysis, topology, and differential geometry, and later played a role in the development of string theory. Professor or Sir Michael is also well known for developing K-theory together with Friedrich Herzbruch. K-theory is the study of flat space and how it moves around and is applied in the study of topology and geometry. Professor Atiyah was awarded the Fields Medal in 1966 and the Abel Prize in 2004, the two highest accolades a mathematician can receive. He served as president of the Royal Society of London from 1990 to 1995. He was knighted in 1983 and awarded the Order of Merit in 1992. It is now my great pleasure to call upon Sir Michael to give his talk, A Mathematician Takes a Radical Look at Physics. Sir Michael.
Thank you. I did not know Robert Brout before this conference, but having heard all talks here, I feel I now do know. And the second thing I want to comment is, why was I, a mathematician, invited to this meeting? And the answer is, because as I grew older, I metamorphosed into a quasi or pseudo-physicist, and my friends thought I kept bad company. That's the way mathematicians view physicists. It changes a bit. Now, there's a time scale I should mention, and one of the reasons I'm sitting down is I'm not so young, and I'm roughly the same age, give or take, with Robert Brout and Peter Higgs. Peter Higgs is a few months younger than me. And you know, the Higgs particle, the BH particle, is maybe difficult to find, and Peter Higgs himself is much more difficult to find. I live in Edinburgh, and it's very rare that you can see him at all. Now, as mentioned, my time scale, just to put you in position, I took my PhD in 1955. And then I went to the Institute for Advanced Study in Princeton. 1955 was a key year. It was the year Einstein died, the year von Neumann died, Hermann Val died, and a few years later von Neumann died. It was the great place, but unfortunately they'd all gone by the time I came, but their memory was still there. Then, as you heard, I got a Fields Medal in 1966, which is a long time ago, and since then I find myself drifting into physics. The key dates, I think, are about 1978, and by the time I became Singapore in 1989, I was hooked. So that was a 10-year period when I became almost convinced myself that I was a physicist. And then I became then master at Trinity College. I became an administrator and friend of the Royal Society. And I thought my days as a researcher was over. So I gave away my books. I didn't expect to come back. And then I finished my role in 1997. And by some miracle, I was resurrected as a mathematician. Now, you might be interested in how that happened. Well, you probably know Michael Berry. He's a very famous, good physicist. And he actually wrote a paper which nobody understood, not even himself. But it was obviously, it had a very interesting content. Coming out of this paper, he identified a mathematical question which he said posed to me. And I found it very intriguing. I thought about that question. I've thought about it deeply for 20 years. And finally, I solved it. I solved it just last week, and the paper about it will appear in 2018. I'll tell you about it. So I've been working on these questions for 20 years after retirement. You know, there is life after retirement, which is useful, something to look forward to. Now, my alma mater, as a matter of course, is Trinity College, Cambridge, and just a few names. Isaac Newton went there, James Clerk Maxwell went there, and Jeffrey Goldstone went there, and a few other people as well. And Jeffrey Goldstone, I didn't know Maxwell and Newton, but I did know Jeffrey Goldstone. He was even at school with me, high school. He was 2 years younger, and I knew him from then onwards. But he's difficult to track down now. Okay, so now I'm going to start. I will come back at the end with some further comments. I came prepared to give this lecture, so you have to ask, you have to produce slides. So I produced these slides, but during the course of this conference, I've attended very interesting lectures, and I've learned an awful lot. So I was going to really tell you two things, what my slides were, and on top of that, I'm going to tell you what I've learned from physicists. And actually, so I'm really going to give you two parallel lectures at the same time. Well, it's difficult, but still I'll try. Now, here is my first slide. You see, I called it "A Mathematician Takes a Radical Look at Physics." And I mean that. I'm a mathematician. I look at physics from the outside, from the point of view of a mathematician. That's not the same as from the point of view of a physicist, but it has merits. Sometimes the person outside sees better what's happening than the person inside. And I'll have to show you that this is actually somewhat true. Of course, I'll explain later on, you get a different perspective. Don't expect me to use the language of physics. I'll explain that. Anyway, here is my first slide. I'm giving a radical look at physics, and I'm going to explain to you, from my point of view, how to look at physics. Now, I think if I press this marvelous piece of technology, yeah. Let us go back to a long time ago. Look, people were worried about something called the ether. Was space filled with an ether? And the ether would be very useful because it would allow for the propagation of waves and things like this. And the question was, is there an ether or is there not an ether? And the famous experimental work of Michelson Morley showed with increasing accuracy that there is no ether. And so Michelson got the Nobel Prize, the first American to get a Nobel Prize in 1907. And there's a picture of him, impressive looking man. You see his powerful moustache. And he did extraordinarily good data, which showed that the deviation got down to 10 to the minus 17, pretty good accuracy. So there was no ether. So that is the Michelson-Morley. Now, in parallel, or unbeknown to Michelson-Morley, there was another physicist, called Albert Einstein. You recognize this is Albert Einstein, young Albert Einstein. And he was developing special relativity. Now, people said that special relativity was based on the Michelson-Morley experiments. But that's not how Einstein saw it at all. Einstein was sure his theory was correct. And Michelson-Morley was just experimental verification, but it was not part of his thinking. He didn't go out to prove Michelson-Morley. He was doing it for totally different reasons. Reasons of interior consistency of Maxwell's equations and so on. So, and the dates are about right, you see. He did his work in special relativity in 1905. And there was, Michelson Morley he got the Fields Medal, the Nobel Prize in 1907. He'd been doing that before, but it was independent. And Einstein said he hardly paid any attention to the Michelson Morley experiment. And that's not how his books tell it. Books are sometimes wrong. Don't believe what you read in books. Now, so that's a quick summary of that bit of the story about the ether. Now, let me take another question. What about space-time? Is it a continuum? Do we live in a continuum? Or is perhaps space-time at very small scales not a continuum? Perhaps it's discrete in some sense. Well, you can discuss this, and there are 2 points to make. One is that if you want to show that there is no ether by using Michelson Morley, you have to assume there's a continuum. If it's only discrete, that doesn't work. So you have this choice. You can either take no ether, or you can, with a continuum, or you can take an ether with a discrete space-time. Now, this is very clearly spelled out by 2 famous physicists, Dawkins and Drell, written a standard textbook, 2-volume on quantum field theory, which I'm sure most of you have read. And in this book, they consider the possibility of discrete models, and are quite honest about the implications. Now, this wording here is my paraphrasing of what they said, but I've checked it out with, Sidney Drell is no longer with us, but I've checked it out with James, and he doesn't disagree. This is essentially what he said. If at very small scales we use discrete models of space-time, then all our beautiful continuum models are undermined. The ether could exist. But as long as there is no evidence that present theory is inadequate, we will go on using our old ways. Hence, we will persevere with our assumption that differential equations provide the mathematical tools best suited for the study of physics. But they're very honest. Basically, they say, if a time comes when there are problems with physics and that we can't solve them, maybe we have to go back to this assumption. So we have to be open-minded. Is space-time a continuum, or is it discrete? And there are 2 different parallel routes. So bear that in mind. That's a very important, and not my observation, is the observation of Dawkins and Drell. But I was very impressed how honest they were. They said, our theories, all our symmetries are so beautiful. We love them. If we had to throw them away and start with all messy stuff to do with discrete things, we wouldn't know what to do. We'd be lost. So, until we have to do that, we'll stick to the old system. And now my first radical thought, I told you I was going to look a radical look. There will be 2 or 3 radical ideas. One radical thought is, perhaps now is the time that Dawkins and Drell feared. Perhaps you should take a deeper look at the evidence and see if it raises problems which require discrete mathematical models. Are there problems in physics which fundamentally mean that you must look carefully at your assumptions? Now this, you might say, is a task for experimental physics. Perhaps with skill, we could combine the difference in differential equations to get the best of both techniques, and that's a task for mathematicians. Can they skillfully move from the discrete to the continuous in a way that everything nicely works out? And I said here, there are the 2. I haven't met either Dawkins or Drell, but most of you probably have, and you will know which is Dawkins, which is Drell, and I think Dawkins is the one on the left, the younger one. Okay, so this is my first radical thought. I leave it with you for the moment. We'll come back to it later, but bear in mind that this could well be part of the answer to the problems of physics. And there are problems of physics. Everybody knows about problems of physics, and we'll come to those later. Now let's take a question. Let us look at what I call the constants of nature. And for example, the fine structure constant. And there are other constants, which are not necessarily constants. They may vary with the energy levels and so on. Now, there's one person who was extremely interested in the constants of nature, and that was Paul Dirac. Some people think it was only one of his cranky ideas as he got an old man. I remember talking to Freeman Dyson. He said, Dirac was a brilliant young man, but he did all his work when he was young. All these crazy ideas came later when he wasn't doing anything. That is wrong. Dirac had the same ideas as a young man and as an old man. He persisted with his idea. And so this is, I think, radical thought B is, well, one way of putting it is, are the constants of nature not actually constants in extreme conditions? You see, we were used to doing things in the lab. The lab is here on Earth. We have certain scales. Suppose you took your lab and you moved it out into the universe close to a black hole. Well, the gravitational field would be vastly different. Everything would be turned upside down. All your normal scales would be different. So, the location in space-time affects your interpretation of the constants. Will still have a value there, but it'll be a different value. And your phenomenology will be totally transformed. So that means you really think more carefully. So he is saying that constants of nature are not constants in what are called extreme conditions. Now, extreme conditions could be the early universe. We're not normally there, but we go there in our imagination. Near black holes, as I mentioned. At very high temperatures, we try to avoid very high temperatures, but if you go close to the sun, you get burnt. And at very low temperatures, also extreme conditions. And on the ocean floor, way down in the deep, and in bacteria, where we have totally different lifestyles. These are what I would call extreme conditions. And it's a generic word, it means lots of things, but it really means that all our constants we talk about will be very much dependent on space and time. Where are you? Where are you in space-time? What time are we talking about? Are we talking about the early universe? Late universe? Where in space? Are we near a black hole? Are we back in a lab? So all these things matter. And usually physicists say, well, we're in the lab. I'm a lab man. I test all the numbers in the lab to enormous accuracy. But what's the point of all that enormous accuracy if everything really is dependent on where you are? You're not doing a universal experiment for the whole universe. You're just doing an experiment for yourself and your team in the lab. And that's a very parochial point of view. So you see, from the outside, you look at things very differently. All the physicists do, they do marvelous calculations with very small orders of magnitude, high precision, but only when you're stuck in your own lab. That's not how a mathematician sees his role. We wave our magic wand and say, imagine yourself in the early universe. Imagine yourself near a black hole. Imagine yourself going through an event horizon. What happens then? So, think of extreme conditions. Where I am in Edinburgh, I have an office in the James Clerk Maxwell building, very appropriately, and outside my room there is a building called Study of Mathematical Extreme Conditions. And there what they do is they can't study things at high temperature because they all frizzle up. They study things at high pressure and in very small scales, what they call diamond anvils. And there they can get exceptionally enormous pressures on a very, very small scale. That is an extreme condition, and they find totally different physics. And that everybody is doing that these days. It's the buzzword. So there are labs especially devoted to that. Now, so that was about this statement. Now, the experiments are very difficult because the deviations that you will get can be very small, typically the order of 10 to the minus 40. And that number, 10 to the minus 40, was one that fascinated Dirac. It was always the same number, or you might be 40, or might be 80, depending what the dimensions are. But basically, there was one very big number, or very small number, which always turned up. And it was obviously, in some sense, related to the difference in scale of the fundamental particles and the radius of the universe. That's what this number means. But physically using it and making sense of it, that's what Dirac really was wanting people to do. And people only use it in a very formal way. So this is really the radical thought due to Dirac. I'm just publicizing it. Dirac is one of, I should say I have a few heroes. I can list my heroes. Well, I'll tell you now. Who are my heroes? Well, Albert Einstein is up there. James Clerk Maxwell is before. And Dirac is alongside. those are my three heroes in physics. And actually, they're not a bad lot. And I have a few mathematicians as well. I'll come to those. Now, let's come to James Clerk Maxwell. Now, James Clerk Maxwell was, I think, everybody knows that he was a famous physicist, but they don't know what he did. They just thought Maxwell's equations are marvelous things, but that's only a tiny bit of what he did. He was a very deep thinker. Well, so you know the other things he did. He studied thermodynamics. He studied color vision. He studied all sorts of things, and he was a very fundamental thinker. He thought very far ahead. He was the father of cybernetics, according to Atiyah. He was a great thinker. And also, I recommend anybody who hasn't read papers by Maxwell, or even his, not papers, speeches he gave to scientific meetings. They are marvelous bits of English prose. He said if you've got a good idea, you can explain it without symbols, without formulae, just by using words. And he did that magnificently. If you read Maxwell, and because he wrote it like that, they last a long time. Those ideas at the time are as valid now as they were then. They're time independent. So Maxwell is a real genius. He died young. He was 47 when he died. But everybody knows, I think it was Feynman who said, in 2,000 years' time, when people look back, the only name they'll remember is that of Maxwell. And I think that was a good description. And there are lots of reasons. People think he only did something. He did vastly more. So now, I put here Maxwell as a young man, because he's going to come here. I wanted to emphasize that the people I'm talking about were both young and old. Some didn't become very old, but some lived. And their ideas, I think, very pertinent even when they're older. So Einstein, I told you, was young and old. Dirac was young and old. Maxwell didn't live that long, but he started off very young. First papers were published when he was 13. So he died at 47. By that time, he was a senior figure. So he had phase shift, but basically, he was also young and old. And he contributed a vast amount. So I'm going to tell you some of what he did. I'm dividing Maxwell up into three parts. He deserves, a trilogy. A, as a mathematician. His mathematics was extraordinarily skillful and powerful. If you read his mathematics, it's elegant, beautiful, and his mathematical models, whether they were discrete or continuous, he said they should be precise statements which have rigorous proofs. So in mathematics, he believed you should put down what you think, prove it, and that is mathematics. And he distinguished that from physics. Mathematics is what you do rigorously. And as a young man, Maxwell did that. Then he said there are two things that physicists are interested in. There are the laws of thermodynamics. The first law is the conservation of energy. He said is a mathematical uncertain. Energy conservation to Maxwell was absolutely fundamental and was really mathematical. Secondly, Maxwell was a statistician. He studied distributions. And large systems, he said, have to be treated probabilistically. And large data can provide increasingly strong evidence. So if you have a large number of particles, a large number of anything, you can't possibly follow the dynamics of all these separate ones. You must apply some probabilistic methods. And Maxwell did that. And he was followed by Gibbs and others. And then he laid the foundations of whatever you like to call it, probabilistic statistical mechanics. So he was a statistician who knew how to apply it in the physical world. And then you come to the second law of thermodynamics, which has to do, with entropy rather than energy, has to do with information. And he says that is statistical. If you've got a large number of particles, then the information you get, which leads to entropy, which means disorder, if you increase the number of particles, it becomes more and more of a certainty. Never total certainty. It's always 99.9, increasing certainty. The probability goes to 1 in the limit. But if you have a small number of particles, or a middle-sized number of particles, of course it doesn't apply. So between single objects, the large number, there is a whole spectrum of possibilities. And Maxwell was fully aware of that. So now, this here I've drawn a picture. I hope you can see it. This is the Maxwell demon. You've probably heard of the Maxwell demon. People think it's unfair to call it a demon. He's actually friendly. But this is a nice little drawing. It was drawn by Szilard, the famous physicist, and it shows the Maxwell demon opening the gate between A and B, where there are particles moving around, and when you're meant to get normal flow backwards and forwards with the heat, you get equilibrium of heat after a while. But Maxwell said, well, supposing there's somebody there watching all the particles, and when he sees a particle which is going very fast, he lets it through. And it doesn't cost much energy. It's insignificant. So that's contradicting the second law. And then there's been a big broad discussion since that. And the normal answer is, well, actually, the answer is that the information is important. Information is part of entropy, work of... and therefore, having some information is actually crucial. So when he sees the particle, Szilard, he is actually using some information. Information is, if you take that into account, then that solves the problem of entropy. That's the usual theory. But actually, a demon is much subtler than that. If you look at it carefully, you'll find that it doesn't really answer all the questions about the demon. Demons, they reappear every level. And I say Maxwell's demon has not been finally disposed of. He is still there, even when you think about Shannon's work and information. It's only part of the story. So there's a lot of subtlety in that, and Maxwell was aware of that. He liked his demon. Actually, he didn't like the word demon. He thought that was unfair. But it's stuck. So everybody knows about Maxwell's demons. And now, thirdly, I put down C. He was a natural philosopher. Now, when I studied mathematics in Cambridge many years ago, it was traditional in Cambridge that you studied pure mathematics and what was called natural philosophy, which means applied mathematics, theoretical physics. The philosophers came in two kinds. In the old days, there were the moral philosophers who studied theology and morality and ethics, and there were the natural philosophers who studied the real world. And all physicists would have been called natural philosophers. Now, it isn't just a matter of semantics. The word natural philosopher carries more overtones. It really means you want to understand the philosophy of nature in deep sense. And I've given here as an example Occam's razor. You've probably heard of Occam's razor. Occam was a 13th century philosopher, and his argument was that if you're faced with a lot of possibilities of trying to explain something, and you should choose the simplest possible explanation, as simple as possible, but allowing to account for all the complications. It's a very sharp frontier. You mustn't be too simple, or it wouldn't explain the world, but it mustn't be too complicated. That's already done with information. So Occam's razor is a very sharp philosophical tool. I've had a lot of discussions with physicists. They say, oh, that's a lot of nonsense, medieval nonsense, forget it. That's not true. Occam's razor is highly relevant, and Maxwell believed fundamentally in Occam's razor. By the way, I put at the bottom a statue of Maxwell. And if you come to Edinburgh, I'll be delighted to show you the statue of Clerk Maxwell. There it is, partly because I was responsible for putting it up. Maxwell was brought up in Edinburgh, Edinburgh boy. He went to school there, university there before he went to Cambridge, and we had a site. Well, I managed to persuade the city council to provide a site for the statue. I managed to find sculptors to do it. I managed to raise the funds to put it up, and that was in 3 years, when I was president of the Royal Society of Edinburgh, that was my achievement. And I'm very proud of that. People just pass it and say, gosh, it's always been there, hasn't it? Hundreds of years? It looks like that. But anyway, when you come to Edinburgh next, go and look at Maxwell's statue and bow and pay your respects to the great man. Okay, that's, well, I mean, Maxwell really, he is my real hero. Well, he went to my same college, the same university in Edinburgh, Cambridge. Now, the next thing is there are what you might call in physics, different regimes. I use the word regime not in a political context. We want to regime change is the functional word, in the sense that it's not a loose word, but basically it means situations where you're studying certain kinds of things under certain circumstances. Different regimes means different energy scale. So it's a loose word, but it captures the spirit. Now, one situation is quantum mechanics is used for particle physics. Everybody here has been talking the language of quantum mechanics about particle physics and other things. So quantum mechanics is about general relativity. Einstein's great achievement was for cosmology. Nobody disputes that. Well, general relativity was one of the greatest inventions of any human mind, and Einstein is justly famous for many things, but general relativity was his masterstroke, and it has remained a masterstroke. What, more than 50 years after it was created? It survived all the possible attacks. It is still there. It is the prime example of pure thought. Didn't depend on experimental data. He didn't have to check his fact figures. He just sat down and thought. And you have a brain like Einstein, insight, you get a good answer. Now, as you know, and everybody mentioned here, the holy grail of current day physics is how do you combine, how do you unify these two fundamental points of view? It's very small, where you usually study with quantum mechanics, and very large, which is studied by cosmology, by general relativity. We want to unify them. People have talked about it, and they pointed out there are difficulties. There are problems. Nobody has done it yet. There are lots of ideas. People think they're close, but I think they're misleading themselves. So this is the Holy Grail. Now there are two points of view. One point of view, which is believed in by people like Einstein, Penrose, Hawking, and others, is that general relativity should swallow up quantum mechanics. In other words, general relativity is the better theory. Quantum mechanics is a small theory. The other point of view, which you might say the orthodox point of view, is the other way around. Quantum mechanics is so well understood, you want to quantize gravity. And that is the alternative. So do you want to quantize gravity, or do you want a gravitational, I don't know, see what I mean? You've got a choice. When two, modern terminology, when two companies merge, one is the dominant partner, they usually take over the other one. So the question is, in the unification, is gravity going to take over quantum mechanics or vice versa? Well, you can guess my answer. Now there's a third point of view, which I called sitting on the Copenhagen fence. Niels Bohr, with his famous complementarity principle, said, well, neither this nor that is both. You know, one day I think of things as particles, the next day I think of them as waves. I'm open-minded, and Samuel says it's a bit wishy-washy. You know, he tried to escape the quandary. But there's some merit in what he said. I think give him a bit of his due. He was actually quite a deep thinker, was Bohr. Now, my next point is to say that when you have many points of view, I've quoted this phrase, I borrowed it from George Orwell, all viewpoints are equal, but some are more equal than others. You probably know the original, and so some are more equal than others, and I think that the view of general relativity is more equal than the view of quantum mechanics. Let me put it that way. Now I've finished this slide with a diagram, which is, there you see it, there it is. It's called the Penrose tribar. Now how many people, put your hand up if you know what the Penrose tribar is. How many people know it? Well, 1 or 2 hands have gone up, but not universally well known. What's the mistake? The Penrose tribar is fantastic, helps the thinking. Well, let me just give you a few remarks about it. It's a triangle. If you look at it carefully, it has 3 right angles. Obvious, look, you can see. Every 2 are right angles. Yet, it says in the plane. How can that be? You know, so that's a contradiction. So that's one of its mysteries. But another point of view is that suppose you're in a room. This is not a very good example of a room. Suppose you're in a cubical room with x, y, z coordinates. If you go along the x-axis, then along the y-axis, then along the z-axis, you obviously climbed out of the plane into three-dimensional space. If you look at this from the point of view of on the long diagonal, if you put an eye there, then that point projects onto the same point, and you get the Penrose tribar. So the Penrose tribar is, if you like, an optical illusion, because the point of view you've adopted is one which is gone out of space. Now, the fact that it's gone out of space is a signal that things are badly behaved. Because, for example, if you keep iterating that, you keep climbing up the tower, which never stops. Have you ever seen the drawings of Escher? I think one of the lecturers showed pictures of Escher, the hyperbolic plane. Well, Escher, and you know the marvelous picture where you have a waterfall, but the water is always flowing down, yet it's always on the same level. That is the Penrose. In fact, Penrose explained that to Escher. Escher took Penrose's idea and turned it into artwork. So Escher's drawings embody the Penrose triangle, a tribar. And I can say much more about it. So this is, don't discard this. Another point of view is that if you've got an algebra, which is, most algebras you're familiar with are associative. But there's one famous algebra that is not associative. That's called the algebra of octonions. You know, you have the real numbers, the complex numbers, the quaternions, and then you have the octonions. And the octonions are not associative. Nevertheless, any two pieces are associative. So you think of it this way, that any two sides of that make sense. Any two lie in a plane, but the whole thing lies in three dimensions. And so the octonions, the non-associativity of the octonions is another explanation of the Penrose tribar. And I claim, subject to another lecture, that the non-associativity of the octonions is related to the difficulties of gravitation. I can answer questions afterwards, if you like. So people who use the real numbers are using the complex numbers. Physicists love complex numbers. Where would physicists be without complex numbers? And they learned, of course, from Hamilton about quaternions, SU2. So where do the octonions come in? Well, the answer is that gravitation requires it. And so the difficulty with gravitation is precisely that it doesn't stay in the plane, and therefore spirals out of control. You can build, even in Singapore, you can build towers of 20 stories, 40 stories, 60 stories, or even Malaysia, but you can't build a tower of infinite number of stories. It's difficult. And so that's the difficulty of gravitation. Okay, that's my point of view. I told you I'm giving you a radical point of view. You don't need to buy it, but I'm telling you, and therefore those of you trying to quantize gravity are wasting your time. Sorry, but I mean, it's helpful to tell your friends point blank that they're wasting their time, so they don't go on wasting their time. Now, I'm going to end with some quotations of mathematical physicists. Einstein was, of course, a marvelous man for quotations. You see, in his time, he was so famous that everywhere he went, the journalists would come around, Professor Einstein, what do you think about this? So he invented the soundbite. The soundbite was a very short statement. And you gave the soundbite, the journalists went away very pleased. Professor Einstein says this. They didn't understand the word of what he was saying, but they knew it was deep. And so what he said to them it was deep, but they didn't understand how deep it was. Anyway, this is one I like. Einstein says, I want to know how God created this world. Okay, we all like to do that. I'm not interested in this or that phenomenon, in the spectrum of this or that element. I want to know his thoughts. The rest are details. That's an ambitious statement, but in some sense, it expresses Einstein's philosophy. And the ultimate aim, I added my own expression, the ultimate aim of the physicist is to predict experimental evidence from the simplest mathematical models. That's what we're all trying to do. We're trying to get experimental data that can be deduced from mathematical models that are as simple as possible, Occam's razor. I think that's a very correct statement. By the way, Einstein another time said that I would like to know what people asked him, what do you think about all the new particles? He said, I just like to understand what an electron is. And I've taken that seriously. If you really understand what an electron is, and one electron and two electrons, then you're well on the way to solving the fundamental problems of physics. And people are still struggling with trying to understand electrodynamics. Now, the next quotation I have isn't on a slide, but I heard it recently from somebody. When Paul Dirac, after he died, 10 years later, we managed to persuade the people who organized Westminster Abbey, all our famous people are buried, to bury Dirac there. I mean, you had to wait at least 10 years, and it was 10 years after he died, we buried him there. And I was there as part of the process. And somebody said that, I think it was an occasion, a quotation of Niels Bohr was mentioned. And what Niels Bohr said about Dirac was, of all the physicists, Dirac had the purest soul. And I think when you reflect on that, it is actually true. You might say he was almost ethereal. But he had, to Bohr, who was, quite hard, he said, of all the Dirac had the purest soul. I think it's a very deep remark. Okay, so I didn't have that when I wrote the slides, so, but now my next one is Hermann Val. Now, Hermann Val was a mathematician, one of my mathematical heroes. But he was also a mathematician with a great interest in physics. And in fact, he contributed a lot to physics. Gauge theories were invented by Hermann Val, amongst other things. Hermann Val did an awful lot of work in relation to physics. And so what Hermann Val said was, my work always tried to unite the true with the beautiful. When I had to choose one or the other, I chose the beautiful. Now that's a remark from a mathematician. You think, surely, mathematicians should always choose the true things. But the answer is that you don't really know what's true. You never reach truth, but you know what you feel. If you see something that's beautiful, you feel it here. So that's actual direct expectation. So my interpretation is that beauty is the torch that guides you towards truth. And that's what Hermann Val was saying. Now, I've translated that into mathematics. The ultimate aim of the mathematician is to fit beauty to experimental evidence. Experimental evidence here can mean nothing in experiment, but also can mean mathematical results. So Hermann Val is undoubtedly in my pantheon. And I once saw Hermann Val in 1954. Now I have quotations from philosophers. I told you about natural philosophy. Here is Bertrand Russell. You've probably all heard of Bertrand Russell, also from Trinity College, by the way. And it says, mathematics possesses not only truth, but supreme beauty. Supreme beauty, kind of austere supremacy. And then he added underneath a comment, which is typical Russell, about Pythagoras. He says, Pythagoras was the most important person who ever lived, both when he was wise and when he was unwise. Now, what he meant by that was that Pythagoras was the first person to realize that music was based on mathematics, and geometry was also based on mathematics. And those are the two most important things at the time. Music was used for all sorts of rituals, and agriculture was dependent on mathematics. So mathematics was the foundation of life. And moreover, mathematics explained things in a way you didn't need to appeal to gods. You didn't say there's a god called Jupiter who strikes thunderbolts. He said there are natural laws, and it's our job to find them. So he was the person who started science. Ever since Pythagoras, we all believe there are laws of nature. What are we doing our time here? We're trying to find out what the laws of nature are. And it's Pythagoras who started that off. Now, what did Russell mean when he said when he was unwise? Well, what Pythagoras did, besides having this fundamental idea, in those days, of course, he also believed in a certain amount of mysticism. He was a bit of a mystic. And Russell was a very hard-headed logician. He thought mysticism was bunk. And so that's what he meant he was unwise. But actually, I think he was hard on that. Mystics have their own insights. And so I think you shouldn't dismiss Pythagoras on that. But Russell was, he liked making these waspish remarks. By the way, if you're a mathematician and you want to get the Nobel Prize, you have to do something, you have to change your field. And Russell got the Nobel Prize for literature, because of course he wrote beautiful English. Right, so that's Russell. Now, I've got to end up with Clerk Maxwell again. There is dates, you see, 1831 to 1879. Here's a quotation from verbatim from Maxwell. And you read it carefully, you see, it's a marvelous piece of English, and it is beautifully written. So I'll read it slowly and reflect on it. The mind of man is like a tree, shooting out branches which adapt themselves to the new aspects of the sky towards which they climb, and roots which contort themselves among the strange strata of the earth into which they delve. Now, isn't that beautiful poetry? Actually, Clerk Maxwell wrote a lot of poetry. So this is an example of his poetry. And there's a picture here. Well, first of all, there's a picture of Clerk Maxwell as a man with a beard, older. This is not Maxwell as a young man, which you saw before. Maxwell as an elderly man. And this is his tree. This tree, if you look at it carefully, has many interpretations. You can think of, first of all, it's an obvious symmetry between, if you reflect, the black goes into white, the white goes into black. That's a kind of duality. If you go upwards, things are getting bigger. If you go downwards, they're getting smaller. It's small-scale, large-scale dualities. This is love. The tree is bifurcating everywhere. Looks a bit like a Feynman diagram or something. I mean, you can interpret this in thousands of ways, and they're all true. So this tree and the English that describes it is a marvelous example of Clerk Maxwell's poetry and the depth of his thoughts. And the fact that he could write a phrase like that without a single formula. I'm not sure if he drew the picture. So the picture is perhaps drawn by somebody else. But it illustrates that verse. So he really was, and you can interpret this in many, many ways. You can fill it in and you'll get hyperbolic plane and so on. Okay, now I'm going to finish off with, is that too small or can you see it? I can hardly see it. It's all right. I told you I've been working on this problem given to me by Michael Berry for 20 years, and I just solved it with a young friend from Beirut, Lebanese. And here it is. It's a very short paper. It's only about 12 pages. And it claims it's a very elegant piece of mathematics. And it has what it's, I think I can read what it says. Well, can I make it bigger? Is there anybody I can magnify this? Who's an expert on? Okay. What? Can I magnify it here? How do I do that? Because I can't read it. Can I make this bigger?
I think we have to exit.
What?
Probably have to exit the program.
I can't read my notes. There's so much use. And I think I want to turn backwards. I think it's getting better. Move it up a little bit more. Yeah, now I can read it. Okay, that'll do for a moment. So this paper, it is called The Relativistic Geometry and Dynamics of Electrons. This is answering Einstein. He wanted to understand what the electron was, and he wanted to understand it fully in terms of its dynamics, and including its spin and all that, relativistically. So now this can be thought of in two ways. Either it's thought of as geometry, in which case it's a mathematical theory, or you can think of it in terms of electrons, which is a physical theory. They are equivalent. There's a dictionary which will swap them around. So when we wrote this, We wrote it, well, on the one hand, it's a purely mathematical theorem. On the other hand, it has a very natural interpretation in terms of physics. Now, the proof of the mathematics does not depend on the interpretation of physics, but it's really ridiculous not to use physical words to help you with your intuition, because we don't think formally, we think by ideas. So here the physics helps the mathematician because he uses the physical language, but that is not part of the proof. The proof is purely mathematical. But conversely, if you're a physicist, you're interested in the physical statement. And the physical statement is a very precise statement. So you get the statement of physics. And if you want to know, it's mathematically sound because it's equivalent to a mathematical theorem. So this is actually getting the best of both worlds. Now, I won't read you the statement, but what it says is, so we made a number of conjectures about configurations of n distinct points in hyperbolic 3 space arising from ideas of Berry and his collaborator Robbins. In this paper, we prove all these conjectures purely geometrically, but we also provide a physical interpretation in terms of electrons. That's a very simple statement. Now, I will go to the end of this. I think I want to do the last paragraph. I think it's what's happened. There should be another page.
Which page?
Well,
Page. Let me.
I gave him a page. What's happened to my last page?
Last page, is it?
Well, I had it. There we are. Can I see this is contracted? Can we make this more legible? So yes, okay. So I end up with this paragraph. I say the relation between mathematics and physics is very deep, both historically and philosophically. It continues to evolve, and there is no fixed frontier. But we will adopt the Einstein philosophy that geometry is ultimately geometry is supreme, and quantum ideas are subordinate. So in this paper, we eschew the word quantum. The word quantum is not used anywhere. It never appears, though supporters of Niels Bohr will spot it lurking in the bushes. So we can write an entire paper about this topic without once using the word quantum. But of course, if you're a quantum physicist, you can interpret it. You can translate it. You just buy a dictionary. And the dictionary, and everything you said here, but you don't need to think fundamentally. You don't think that way. You don't think in terms of expectation values and Hamiltonians. You just think differently. You think mathematically. You think geometrically. You think like Einstein did. And that way, you understand what you're doing. And you know when you can do it, what the difficulties are when you can't do it. So I think, now I've written half a dozen papers, of which this is just one, all of which have the same sort of philosophy. The word quantum is not used. I don't like the word quantum. I use the word, you can have manifolds, and manifolds of positions, and the number of dimensions can vary, and on the manifold there are waves, and the waves propagate, and that's wave mechanics. And in fact, the closest bit of physics to what I've been doing is what's called the de Broglie-Bohm theory of pilot waves, which is known to be mathematically equivalent to quantum theory, but has a totally different ontology. And so this is actually in the spirit of Bohm, de Broglie, but mathematically complete. And that theory got stuck in various places. They couldn't solve various issues. They couldn't make it fully relativistic. They couldn't do this. And I claim that we can do that. And I end up with one final remark, is that physicists think that mathematics is a rock. If you can get a theory which is rigorous mathematically, that's very good for physics. You can't necessarily do it, you approximate, but ultimately physics is meant to be built on mathematics, which provides the rock. That's a mistake. If you ask mathematicians, they say mathematical foundations are not on a rock. Everybody knows that Gödel and people prove insolible theorems, so mathematical foundations are very shaky. So mathematics is on equally shaky ground. So, and in fact, you have to become a logician to study Gödel's theorems. There are theorems which are insoluble. But what does insoluble mean? It means it's insoluble with a certain set of axioms. If you buy some more axioms, you can go further. And that's a process that never stops. So this question of mathematical logic, because mathematics is the rock on which physics is supposed to be based, actually feeds back into physics. It is relevant to physics. So questions about hard questions in physics, like gravitation, are fundamentally, I believe, insoluble in that Gödel's sense. So the mathematical foundation, whether you like it or not, you can't avoid the shakiness of mathematical foundations, because all physicists use mathematics. And they think, ultimately, that if you've got a good mathematical framework and know it, you solve the problem. Not true. Okay, I'll stop. Thank you. No idea whether I exceeded my time. Probably did.
You want to take many questions? We don't have much time.
I'm happy to answer questions.
Maybe I'll put it in the dilemma to them.
Yeah.
We have a dilemma. We could have a free flow of questions and answers and forgo our lunch, no lunch. Or we limit the number of questions and maybe we can still have lunch. Would that be all right?
I think a few questions.
A few questions, okay.
I don't want to deprive you of lunch.
Yes. Okay, so, I see, okay.
Yeah, you brought up Gödel here, and we discussed it the other night. And of course, physicists never think along those lines because we believe, that we can solve everything and that we but so that's one aspect, that interesting to hear what you think about it. I was also thinking about another one, and that is when David Gross, when he gives these public talks, it's always ending up, with the sort of the limit of the brain. So how much can we understand? Is it so that we at one stage we will reach, and there will be systems by which the brain cannot really solve those things?
First of all, it is very interesting to study the brain as part of evolution. That we have evolved through evolution to have a brain that we have. That's a very interesting question, but that's quite different from the logical foundation. I claim that the logical foundations really means that problems which are insoluble, I think in some of the talks we heard, see, physicists use different language, but I think in Malcolm's talk over there, he talked about things being, what was it? You weren't sure the superfluous or necessary, there was a bit of a gap. That was another way of saying the same thing. Things were uncertain in fundamental sense. You didn't know whether you had to have extra states or not. And so that's the way physicists would see it a different way. But fundamentally, it is to do with insolubility. And mathematicians have got used to the fact that large numbers of problems are insoluble. And physicists, if they want to do mathematics, had better get used to the fact that mathematics does not solve all their problems. But if there is a problem, it will be relevant to a physical problem. And the physical problems, we've heard, there are lots of them. Every talk here ended up, we don't quite know how to do this. Well, the answer may be, you can't.
Maybe we have one more question. Will it be all right? I don't think we want to forgo our lunch, right? Okay.
No.
I think as a physicist, I should give a talk. A physicist takes a radical look at mathematics.
You're perfectly entitled. I believe in symmetry.
What I want to know is what's your point of view about infinity? Because I have a feeling that the problems with Gödel and other related questions in mathematics have to do with the fact that these theorems are often circular. So, of course, when you introduce circularity in your mathematical arguments, then there's a danger.
That's not the issue. It's not the difficulty with mathematics is undoubtedly to do with infinity. The infinity of relevance is the infinity of real numbers. What is a real number? And real numbers are what physicists think they understand. But you don't know what real numbers are. You can write down lots of numbers, but how do you know you've got them all? And so this question about the infinities, which are present in mathematics, they appear in physics in a very real way because we don't know what you're talking about when we talk about real numbers. If you can't talk about real numbers, what's physics doing? It's using real numbers all the time. And if we don't know what a real number is, your foundation is shaky. Now, the question of what is a real number is a very difficult question. You can write down algebraic numbers and so on. You can start filling in all It's like putting pixels on the screen. You can keep putting more and more pixels. You won't get a continuum, but you get something effectively. So in some stages, physicists will say, oh, I don't care. I don't need foundations. I can just wave my hand. And so, all right, you brush it under the carpet. But if you brush it under that carpet, it'll come out of that carpet. If you really sweep things underneath, you'll pay the price. So you better be honest and say, we can't solve all these problems. And we have our limitations. It's not the human brain is limited. It is the inherent reason, logical apparatus that we use to think, which is much more fundamental. So eventually you put your hand up and say, I can't do it. I pray to God.
Thank you. Maybe we should, yes. So let's put our hands together to thank Sir Michael.